Okay, thank you very much for coming today in this nice presentation, the first one, hopefully. So, the first thing I have to say that this presentation is the presentation from contribution for different people from my group, our group, Biosignal Analysis for Rehabilitation Therapy group, and the research group is at the UPC in Barcelona. And I will try to talk a little bit about EEG recordings, particularly about, to remember very quickly basics on EEG, but moving later to the event-related potentials, the experiments related to this kind of potentials, because also they will be associated with brain connectivity, which is the main topic of the speech. Okay, this is the outline. Let me take that, because I usually speak too much. So the outline of the presentation, first, as I said, three slides about EEG recordings, moving to event-related potentials, to go to the main topic, which is the brain connectivity, with different ideas or concepts. What is brain connectivity, EEG connectivity, examples of case studies, graph theory, and examples. Some of them from studies from my group. We start with the EEG recordings. So, well, for sure you know that your brain is always active, even during sleep, even in resting state, even now, that maybe you are not very alert. So if you don't have any activation in the brain, it's because you have a problem. So we have billions of neurons connected to each other inside our brain, and this activity is propagated from different tissues, also from the bone, the skull, the skin, and we can record this activity by electrodes on the scalp. Okay. In this process, there is many effects, like attenuation, but also the activation is propagated and is spread to different areas. This is a problem that is special important in brain connectivity, as we will comment later, but we can start and talk in advance. When we, in the next slide, we will comment about the number of electrodes that we usually use for the EEG recordings. Okay? But in any case, we record this EEG activity, and by neurophysiologists, we have recognized different rhythms. We can see here the different rhythms from low to higher frequencies. This is the delta band, this is the theta band, this is the alpha band. In the alpha band, we have the mu band from 10 to 13 hertz. This is especially important. Some ideas we will comment later. And finally, the beta band. Okay, beta band more related to the mental processes and cognitive procedures, etc., where we are especially interested in these studies. We have here the power spectrum, and well, all of these bands. We can use just a few electrodes, especially in children, 8 electrodes, for example, newborns, etc. And also, we can increase the number of electrodes. When we started, or when I started analyzing EEG, usually the number of electrodes were 19 electrodes, which is this picture. Okay, we can see here in the central, in the middle, in this C8 channel, more frontal, F8, and then it goes back. This is the parietal P8. And the other ones. This is temporal. We can see, okay, you know, this is the nose, the ears, It's looking at from the top, looking the head from the top, and also parietal, and also on back the occipital channels. Okay, but thanks to the improvement of the technology, the cost, etc., now we can record much more channels until 128 or even more. Okay. Maybe you can consider that, okay, if it's possible to have more electrodes, it's much better. Well, theoretically, for the sailor, for sure, because it's more expensive. But there is more redundant information in the electrodes if you have a lot of them. And also, you have many electrodes, the effect that we commented before is more important. For example, this is the balloon conductive effect, okay? When you have an activation, for example, a dipole inside your brain, and this is propagated, and the activity arrives to different points from your head, and you put the electrodes, but it's not clear if the information is coming from one side to the other, or this is from propagated potentials, not from potentials going from one point to another one. So this conductive volume effect is very important when you have a lot of electrodes. My recommendation is 64 channels, it's okay, and to have more probably is not necessary, and you can have more problems. Well, the bandwidth of the EEG, as we saw before, from delta to gamma even, well, we didn't mention the gamma band, but the gamma band even can arrive to 150 to 100 hertz, okay? But, well, it's not very common to analyze the gamma band, but in this case, you can use a higher sampling frequency than this one, okay? But it's not necessary a very much higher sampling frequency. When I see a study and they record 2 kilohertz or 5 key for the sampling frequency, probably I think, okay, maybe you don't have a lot about EEG recordings, so, because it's totally not necessary. Well, the resolution, as in any potential, 16 bits or more bits, it's better. Also, in the, well, we didn't mention in the previous slide, the reference. Usually, the reference is the mastoids here, behind the ears, and we put a couple of electrodes, and the average mastoids is the usual reference. But then we can have another reference. This reference is to increase the common mode reduction rate in the acquisition. So we can use, for example, the CIS8 for the reference electrode, so all potentials are referent to this activity. In other cases, the reference is the common average. So we try to enhance, to highlight the differences in each electrode with respect to the common average, especially in testing for even-related potentials, later. So, well, depending on the montage of the acquisition. Well, high input impedance, as you know, well, etc. We can move to the even-related potentials. We can see just an example of experiment. When you receive a stimulus, there is a special activity in your brain, okay? Usually, as I commented before, your brain is always active, so you have like the EEG background. But for this stimulus, you have an additional activity what is associated with these event-related potentials. The name is very clear, no? Potential related to this event, it is a specific stimulus. These stimulus can be cognitive events like visual, auditory, etc. But can be also motor response if you move your arm or your leg or everything. Or even if you think to move something in your body. Also there is a response from your brain. And also the stimulus can be an electrical stimulus or magnetic stimulus. This electrical stimulus produces somatosensory evoked potentials. For example, if you stimulate the median nerve, for example, there are specific potentials in your brain. We collaborate with a startup in Barcelona. Where are we from? For example, they are analyzing a specific potential, which is called N20, because this potential is very useful for the surgery of patients with a very recent ictus, stroke, because the success of this surgery is around 50%, and they want to increase this rate. Yes, identifying this potential in the brain, because this means that you can continue in the surgery with high probability of success with the patient. Otherwise, it's better to stop the surgery and to wait for another moment, for example. Even when the patient arrives to the hospital, this is possible to monitor this potential in your brain in order to know if this patient must go directly to the surgery room, because you know it's crucial, the timing in stroke patients when you have a stroke. So these potentials comes from as a response of a stimulus. So you have to analyze this potential time locked to an event. Okay? This time locked must be for the stimulus or even the response. Okay, we will talk a little bit later. And remember that these potentials are embedded in the EEG background. Probably you know that the name of these potentials is a letter, capital P or capital N, depending on if it's positive or negative. But positive or negative, not the value, but the deflection. For example, this is positive and this is negative. Even the value is not negative, it's positive, but the deflection is negative. And the number after the letter means the time more or less after the stimulus the potential appears. For example, this 200 milliseconds after the stimulus. Okay, you can say, but well, this is P2 and this is N2, so cannot appear exactly at the same time. Not exactly not, but more or less, approximately after the stimulus. So for these potentials, well, the first feature that we can calculate is the peak. For example, this is the P3. It's more or less after 300 milliseconds. This is a very well-known potential and very analyzed for in many research studies. And the peak and also the latency, which is the time after the stimulus, the peak appears. Okay. There are other potentials related, for example, in the experiment, the response is wrong. You realize that, okay, this is wrong, and very quickly you correct. There is a specific potential associated with this phenomenon, which is called the error-related negativity potential, the ERN, for example. And also other options like the go and no-go experiments, when you have to do something, and at the end they say, no, you don't have to do it. This is an inhibition, and it's related to other potentials. We can classify these potentials in, well, in two groups, the exogenous and endogenous. The exogenous are the potential very early after the stimulus. They are more related to sensory processes. You don't have time to think about the stimulus. Just your brain, your body receives the information, and this is something coming from the environment. So these potentials appear before 100 milliseconds or until 100 milliseconds after the stimulus. And we have the endogenous potentials later after 100 milliseconds, and they are related to specific cognitive processes or mental tasks. Okay, you are processing the information receiving from the outside, and well, they are especially interesting in cognitive disorders or neurodegenerative diseases, etc. Especially, as I said before, the P300 or P3, which is very interesting in order to evaluate the peak, and also if there is a little bit later as usual because of the specific disease, for example. And we don't have to forget that also the potentials are affected not only by the experiment but the whole environment or other things additional to the experiment. Okay, we can see in this slide that, okay, I showed this potential very clear here, but really this is not true, because there is a lot of noise because of the EEG background. For example, we can see for each color different trials. Okay, trial or repetition is the name of each stimulus you produce in the experiment, because this phenomenon is repeated a lot of times, dozens or even hundreds of times. So in this signal you cannot see anything as I mentioned and I showed before, because of the EEG background. Each color is each trial. Here is the stimulus. Okay, this is an auditory. Auditory stimulus, and well, every trial is from your mother and your father, from his mother or his father. So if we average align with the stimulus, we can observe the same signals after averaging 10 repetitions in blue, 20 in red, 30 repetitions in green, in pink color we have 40, etc. And we can observe that we can see here these potentials as I showed before because of averaging. Okay, and the potentials are smoother because of increasing the number of trials. It can be shown that the signal-to-noise ratio is increased the root square of the capital N times in amplitude, in root mean square, being capital N the number of trials. Okay. This is possible because the EEG background is not aligned with the stimulus. It appears at any time. So if you average many trials, you can consider that this noise, this EEG background is cancelled. Okay, because sometimes it's positive, sometimes it's negative, the potential at the time instant. But what is related to the stimulus is always present in the trial. So when you average, this remains in the average potential. Okay, so in this analysis we have two approaches. Okay, this is the different trials with the different EEG channels. The first approach is to average, as I mentioned before, average potentials, and the other approach is single try analysis without averaging. Okay? If we perform what I said before, we average, we have the potentials, then we have the feature extraction, can be the peak or amplitude, the latency. Also, you have information from different channels. You can use other techniques like source localization by different methods. This is not included in the talk, but open sources like Informer or Loretta, etc., can be used in order to calculate or to estimate the inverse model in order to localize this source inside your brain in 3 dimensions, which is later measured in the EEG recordings. But we can use not averaging, but single try analysis. You don't average, for example, time frequency representations. You can observe or calculate different features, and then we average at the end in all trials, the feature in all trials. So the average is at the end. Okay. Well, in this case, this is particularly used for brain connectivity. When you don't average, and we will explain later why, no? But we don't average from the beginning because we remove or reduce some interesting activity that we can observe previous to the average. Okay, I will explain just an experiment which is called the Erickson-Flanker task. This experiment is, okay, you can observe in your screen 5 letters, different options which can appear on the screen, and also you ask the user or the patient well, to respond with your left or your right hand depending on the letter, H or S. Okay. The other letters before and after that can be the same. This is the congruent case, or can be different. This is the incongruent case. We can expect that this is a little bit more difficult. The same for the other letter in the middle. Okay. In this case, it was possible to, if you realize that you are wrong when you respond, very quickly you have 100 milliseconds or something like this to correct. And if you correct, the ERN appears. This potential that we mentioned before, this is very close to the response. In this case, the time locked is not from the stimulus, it's from the response. Because when you touch or you press the button, for example, with your left or your right hand, so very quickly you realize that, okay, I'm wrong, and you correct. So you have to align, not with respect to the stimulus, but the response. This is the latency, and it's very short. Okay, this is the ERN. We have here, each row are different channels. This is the central channel, EEG channel, the C8. This is more frontal, F8, and this is the parietal, P8. Okay? And this is for the P300 study, is stimulus locked. In red color is when you have the stimulus. And more or less, in 350 milliseconds, you can see the P300. Okay. Depending on the channel, better or worse. But this is the congruence cases, and this is the incongruence, just to compare if there is any influence in the potential. And this is the ERN. Okay, the ERN. We can see very clear, for example, in the C8, the ERN potential, but not here in the other channels. Well, a little bit here in the frontal, but not in the palatal. And for each color, we can see the number of trials or repetitions considered in averaging. In blue color, again, 10 repetitions, 20, 30. This is in red, green, pink, black. Okay. The effect of smoothing. For example, in 10 repetitions, we can see here that it's not so clear the P300, but it's not so bad, no? It's not smoother. For example, if we calculate the maximum, the problem is, okay, the maximum is here, is here, is here. Probably it's better if you have just a few trials to smooth later the potential with a low-pass filter in order to calculate the peak, in order not to be so sensitive to these spurious peaks. High frequency is not always smooth because the number of repetition is not so high. This disappears, this problem disappears when you have more repetitions. But the question is, how many repetitions do you need? It's a very important question, especially when you have the experiment for children, for example, or you have to perform several experiments, because for the preparation maybe you spend 20 minutes or something, and so you prefer, okay, if we can perform 2 experiments instead of 1, we have 2 papers instead of 1, so probably it's much better, no? So you cannot extend a lot, or you cannot. You can, but in any case, with some children with cognitive problems, it's not possible. But even in adults, it's a problem, okay? Because of fatigue of the patient, you have to consider resting times between blocks in order to avoid fatigue, etc. So the question is, how many trials? Well, my opinion, depending on the information you want from the potential, okay? For example, if you want magnitude, peak, or latency, you can perform previous experiments in order to check, not only one, but several experiments, in order to check, okay, if you calculate the peak using from 10 to 500 or 50 repetitions, in this case from 3 channels, the F8, C8 and P8. So we can observe that for sure this is very depending on the number of trials. So I don't believe this value. For me it's not a true value. So if we have more or less with 200 trials, more or less the same value for the peak and also for the latency, this is because of time resolution of the sampling frequency, but it's relatively very clear that it's, with a low number of trials, it's enough to observe the latency. Here, the even related negativity potential, we have something like similar. In this case, with 50 repetitions, maybe it's enough in order to reach. We don't have a different value with 50 repetitions or with 100 repetitions, so why we have to extend the experiment? Okay. In this case, the point is that, for example, you can see here, this is the P8. If you remember, there is no potential. This is why, okay, we can calculate always the maximum, but the maximum is very small, and even it's not positive but negative. So this is why the time instant where the minimum or maximum appears, so changes a lot. This is because really there is no potential here in this channel. So with this information, with all channels, we can have topographic maps. In this case, we can observe in yellow the highest peak of the P300 located around, okay, we observe the C8 and also the P8, etc. This is for the congruent case, and this is for the incongruent case. The values are not very, very different, but the localization, we can see that this is a little bit different. It's more occipital, more posterior, the localization of the case of incongruence than congruence cases. In the even related negative potential, the ERN, so in C8, but also not in the P8, but in the F8. Also, the time alignment is very important. Okay. Well, I did some. I play a little bit in order to disalign the time locked, the stimulus locked. The blue case is the correct case, okay? But in red color, I change it randomly with a Gaussian distribution with 10 milliseconds in the standard deviation. But 10 milliseconds is just if the sampling frequency is 200, is maybe 5 samples, just 5 samples, okay? So a little bit before or after the stimulus. And not always, it's just the standard distribution, sometimes it's slower. These 20 milliseconds. And we can observe that, okay, the potentials in P300 or even in the even-related negativity potential, well, we cannot see the potentials because of this disalignment. Okay, so this is very important. Well, you can see the well, but this is well, not the problem because you have exactly the sample where the stimulus appears. Well, depending, because the visual stimulus is in the monitor. The monitor has a frequency of 50 Hertz for the refreshment. So 50 Hertz is 20 milliseconds. So you can order by the software in the computer, okay, show the stimulus, but with an uncertainty of 200 milliseconds, 20 milliseconds. And 20 milliseconds is the black case. So it's not a stupid problem. It's really important. Well, we have here another example, is the visual voltage that we can observe the same picture, but in some cases, and the target is a special picture, when you have a special potential that we can observe. If we increase the number of, this is the potential in the blue color with respect in the target with respect to the other pictures, what is the normal picture. Increasing the number of the number of trials, we can separate more the potential with respect to the other cases. And just to finish this part, here we can observe potentials associated with the movement. Okay, it's really very, very interesting. This is from Marta's article. So we evaluated in a public database the movement-related cortical potential, which is the potential associated with starting the movement. Different tasks: flexion, extension, pronation, supination, hand open and close from Durara. So we can see the onset of the movement that before the movement we can have this potential preparing or planning the movement. Maybe 1 second before, okay. It's missing the second term. 1 second before and after 1.5 seconds later. Okay, this is the movement-related cortical potential. In different movements, sometimes are relatively similar, not so high. Hands open and close, it's much smaller, this potential. Probably because the movement is more distal. Okay, if you flexion and extension, pronation, supination, and finally hand open and close. Probably because if it is more distal movement, the potential is lower, but this exists. There are also two rhythms, very well known. What is the event-related desynchronization and synchronization? When you start the movement, there is a desynchronization, and when you finish the movement, there is a synchronization. Here we can see in the onset and in the offset at the end of the movement. This is for the mu band and this is for the beta band. Okay. These bands are especially related to the movement, and we can observe this desynchronization at the same time as the movement-related cortical potential appears. And this is maintained more or less, in this case, during the movement, and disappears with a synchronization at the end of the movement. So we can see here the three movements, not here, but also flexion extension, pronation supination, and also hands open and close. And for the beta band, this is something more or less similar. Well, what happens if you don't move, but you imagine of movement? This is the motor imagery. In the case of motor imagery, maybe you can think that, okay, there is no potential because finally you don't produce the movement, but this is not true. For example, in red color, this is the potential for the same subjects for motor imagery with respect to motor execution in blue color. The same, the different tasks, always hands open and closed, not so easy to identify, but it's relatively clear. And there's a smaller potential, okay, in red color, but it exists. Even desynchronization and synchronization, when the movement appears and disappears, well, it exists, especially in mutabands, the same desynchronization. Probably is not so consistent during the imagining the movement than executing the movement, but more or less it exists. It's not so strong in beta band, okay? And also, we can think about what happens with an injury. If you have, for example, a complete spinal cord injury. So also, this injury affects these effects or these parameters or these rhythms. This is also from Marta in a conference from the ethical 2 years ago. So we can observe, in this case, supination, pronation, and hands open, the potentials in red color for patients, in blue color for healthy controls. So the potential is very clear, okay, even with the injury. But we can observe that maybe it's not so strong or so high the effect of the desynchronization and synchronization, okay, in move and in beta band, okay. Obtaining the information of the peak of the magnitude of the potential and also the deflection here, the synchronization, and also the synchronization, etc. We can observe these topographic maps. In this case, comparing controls and patients for each column, controls and patients from three different movements. So in this case, supination, pronation, and hands open. We can observe in controls that the potential and also this desynchronization and synchronization are relatively localized on the brain. In the case of patients, we can observe that it's not so localized, and it's a little bit more spread on the brain. The same in the pronation and also in hands open and closed. This is very clear, the potential. So we can analyze the effect of injury in this during a motor experiment, also from the EEG signals with this kind of information. Okay, so we can move to the single trial analysis. In all previous cases, we average many trials in order to obtain this good potential, these nice potentials or rhythms, removing the EEG background, which is the noise. But we have the option of the single trial analysis. Why it's important, the single trial analysis? When you average, you remove the higher frequencies, because the potential resulting from the averaging is smooth, okay? So you lose some information, okay? You lose some information, can be very interesting. And we can also obtain from from one trial or a single trial, okay? Also, single trial analysis is not affected by the number of repetitions because, well, you don't need a lot just to average all of them in order to have a nice potential. With single trial analysis, well, it's not so relevant the number of trials, which is an important issue, as I mentioned before. And also, we can observe other activities not related directly to the stimulus, which they are removed when you average. So in this case, if you don't average, this is maintained in the signals. And also, what is very important, the phase-based measures, like for the brain connectivity, can be calculated later in single trial approach, because we maintain the phase information of the EEG signals. Okay, when you average, you remove all of this, and you don't have this information, which is very important for brain connectivity. So this is the single trial approach. You have different trials. You calculate time frequency representations, scalograms, spectrograms. You define several features. You calculate this feature for each trial. And then you can average and also to represent in topographic maps, in bar diagrams, etc., or box plots. So this is the single trial option. Okay, we can move to the brain connectivity. I have to stop 10 o'clock, maybe, no? Or not, for a break. 45? Well, I continue. So we can, because I don't have time. Is not Alestania? Well, I continue 5 minutes. Brain connectivity. We move to the brain connectivity. We mentioned in the single trial approach, and we will explain a little bit about what is brain connectivity, different techniques to evaluate the EEG connectivity, some examples or studies using brain connectivity. We comment a little bit about the graph theory, graph theory parameters, and finally some examples from research studies, articles, and also from our group. So what is brain connectivity? Well, so we know that all billions of neurons, each neuron is connected with many of the neurons around or even in further position. And there are two mechanisms, they are called segregation and integration. Okay, so the segregation, when you can have separated zones connected inside of this zone, grouped together, the different neurons, and also integration, when these zones are activated in coordination. Okay, so it's possible to have separated, segregated zones, but also connected to the other segregated zones as an integration. Okay, so they are compatible. And all of this mixture creates the brain connectivity. Well, the strength, the intensity of this brain connectivity, the localization, etc., it's very important. And also, this is a dynamic effect. As you know, well, the brain is dynamic. For example, during sleep, we have different sleep stages. When we are awake, this signal has high frequency components, well, high frequency in the range of the EEG signals. When we start sleeping, the stage 1, we have the theta waves from 4 to 7 hertz. And then we move to the stage 2. Okay, in the stage 2, in this case, we have sleep spindles, but they are produced, they are physiological and also produced by drugs or also by pathologies, but with between 1 and 2 seconds duration, with high frequencies, higher frequencies from 11 to 15 hertz. Also K complexes. So these events permit to the neurophysiologist to consider this epoch to stage 2. And then if you continue sleeping, if you are lucky, you don't have to go to work, you will get up again. So we have slow wave sleep with very delta activity, okay, from 0.5 to 2 hertz. Okay, so even during the sleep, the brain is dynamic. This is changing. So the same effect is in the connectivity. The connectivity is not something fixed during the experiment. This is something that probably changes along the time. And also, not only during the experiment or during the day, also during your life, okay? So, the beginning, the newborns, explosive growth in the brain, connectivity, later protein refining, pre-adolescent consolidation. Well, we can think about other effects in during this stage, but also in the brain consolidation is, I was thinking about my daughter, the consolidation of the brain connectivity. When you are adult, integration and efficiency, and at the end, we are approaching to this state. So the loss of neural connections, not only the disease in neurodegenerative or cognitive problems, but also, yes, normally you have white matter tracts, etc. There are 3 types of brain connectivity. Anatomical, functional, and effective connectivities. In the case of anatomical connectivity, is just, okay, different, one region related to another one. This is very simple. This can be measured, for example, by structural MRI, very clear, for example. And also in this case, this information is not changing so much during the time, because the structural MRI will be more similar today and tomorrow, for example. Here we have the DTI image, DTI, what is the diffusion tensor image, with colors, the different regions related. Well, measuring the water flow from one side to another one, but not directly from the neuron's activity. I think it's okay, it's useful, but well, the point is that we have billions of neurons. So, well, this is a good approach, but it is not for me, because I work in the other one, so I prefer this other two. Functional connectivity and effective connectivity. Functional connectivity, okay, as engineers, we try to analyze statistical relationships in different brain regions. So in this case, well, very simple. We touch one electrode and a second electrode, and we try to analyze the interaction, statistical dependencies between them. So we consider that we analyze the connection between the region of one electrode with respect to the other. So this is the functional connectivity. In the effective connectivity, it's more interesting because we can consider the direction of the flow or the information moving from one electrode to the other one. Okay, so because the directionality of the connectivity is considered in this effective connectivity. Usually these methods need information from past samples of each channel, okay, because it is something that, okay, depending on the past, how the direction of the connectivity is moving to the other channel. Okay, so now maybe we can stop, probably. We will talk a little bit, if you come back from the break, different techniques for EEG connectivity, examples, graph theory, and more examples. We will start in the second part of this talk. Thank you for coming again. So we'll try to explain some techniques about the EEG connectivity. So there are different approaches. The problem that this session is recorded, but in any case, I can say that there are, I don't know, hundreds, but dozens of techniques for analyze the connectivity. And sometimes with different opposite results. And also, okay, the theory say that, okay, this technique is better than this one, but this second one is also continued used in the studies. Why? Maybe the results permit to separate very well controls and patients. So it's a little bit tricky that you try many techniques and finally you select the most appropriate for your convenience, no? But well, it's a difficult field of study, brain connectivity, okay? And also, if we are engineers, we are able to justify everything, okay? This is recording, no? But well, no. We can classify these different approaches for brain EEG connectivity, linear and non-linear. You know, okay, linear. When something increases, the second increases as well with different velocity, but linearly. But non-linear is not so nice when something increases. Maybe the other increase as well, but not linearly, exponentially, or so it's more complex than non-linear than linear, sure, no approach. We can classify the techniques in model-based or model-free. In the model-based, they are parametric, and you use specific models to analyze the typical parametric models to analyze both signals. Remember that we have two EEG channels to evaluate or to measure statistical dependencies between them. Another classification can be in time domain or frequency domain. Frequency domain is especially interested in brain connectivity because remember that these statistical dependencies is not only for EEG, so for any biomedical signals or any signal. For example, we have used them for cardiorespiratory interaction, the hair and the breath. Breathing, also interaction between respiratory and respiratory muscles activity, coordination when you have a pulmonary disease. So it is very open, no? But in this case, it's for EEG. But in these two channels, it's especially interesting in the frequency domain because the neurophysiologists have classified very well the different rhythms we mentioned before: delta, theta, alpha, beta, gamma. But also there is a third option with this information theory domain, okay, more related to the entropes, for example. This is can classify. Pairwise and multivariate. Well, we have worked always selecting a couple of EEG channels, but it could be possible to evaluate not only two, but a group of channels as multivariate. Again, static and dynamic, no? It's clear that it's much better dynamic, no? But well, static, for example, in the correlation, the Pearson coefficient, in the correlation, you have only one value from two signals, only one value. But if you calculate the cross-correlation function, so you have not only the information of the Pearson coefficient, but also the information with the time lag dependency, for example, no? Because it's better if we have something dynamic, a dynamic approach. There are a couple of tutorial reviews for brain connectivity, very interesting. In the first one, we have this classification, the taxonomy. Well, in this case, I would remove this functional. The connectivity can be non-direct, non-directed or direct. In this case, directed would be effective because the direction of the information is important or is considered. And non-directed is because you measure only the dependencies between two channels without consider any direction. For me, this is functional and this is effective connectivity. But well, in any case, this is the tutorial. Here, model-based, model-free, model-based, model-free, correlation, mutual information, cross-correlation, random causality. Well, cross-correlation for me is here. I don't know why they put, because cross-correlation is non-directed. But this copy-pasting from the article, from the tutorial review. And transfer entropy, this is clearly model-free and also directed. And this is in time domain, also in frequency domain. We have other techniques, coherence, very well known, classical functions, phase looking value, phase slope index, parametric and non-parametric causality, etc. in frequency domain. But also in this time domain, we can filter the EEG signal with bandpass filters in specific bands, and then we can measure the connectivity in this band. So it's possible also to use them in the, but with a specific restrictions that I will comment later. There is a second tutorial. This is a mistake. 2023. And this is more recent article, tutorial review, and also from one of the co-authors, the most brilliant mathematicians I have ever met. So I recommend this one. Okay. Well, we can start with the cross-correlation. Very well known for everybody. The first time this was used in connectivity, not in EEG, but also in MRI, in this article. And we can observe a statistical connection between the dynamic activity. No? It's very clear, the cross-correlation. The alternative of cross-correlation in frequency domain is the coherence. No? The coherence is a classical function, but even now relatively used in research studies in EEG connectivity, especially when you want to compare one technique with a new one. You use the coherence. The problem is when the coherence presents the same results as the new one. So you say, well, maybe there is no additional information with these other more complex techniques. But well, in any case, the coherence, this is the formula. Okay. So this is the Fourier transform. Okay. This is the Fourier transform from two signals. This is the magnitude and this is the phase. Okay. Maybe it's not, it's a little bit difficult to understand, but if I put this one, it's more clear because this is the cross spectrum, the numerator, and the square root of the product of the outer spectrum of the two signals. Okay. It depends on the amplitude and the phases of each of both signals considered of components in the cross spectrum, Usually you calculate the magnitude square coherence, which is the model, the magnitude of this. So this is a real value. And it's interesting for neurophysiologists' point of view because we can calculate in the coherence specific bands and the average of the values of the coherence, we can compare, etc. But the coherence is a complex function. So we can calculate other measurements like the slope index according to the derivative of the phase of the coherence and also the imaginary coherence, taking into account only the imaginary part, not the real part of the coherence. Well, in this case, both measures are better because they are not affected by the conductive volume that we commented before, which is an important issue in brain connectivity, okay? In order to be sure that when you relate two EEG channels, well, to be sure, in order to reduce the effect of that, what you are when you are obtaining the dependency between two channels is because there is a transmission or a relationship between these two areas, not because they come from a specific source inside, which is propagated and reach these two electrons. Okay, so this propagated information, when you want to remove, is associated with the real part of the coherence, and the imaginary part is more related to this connectivity. On the other side, if you don't want to consider the phase, you can obtain the amplitude envelope correlation. This is affected only with the amplitude of the time series. For example, we have two signals, and we can obtain the envelopes. Okay, this is from a Saul report. I forgot to put here the reference, but we can calculate the envelope, so we obtain the relationship between the red traces. Okay. But it's much better if we analyze the phase of the signals. It's curious because I teach in my university the basic course of signal processing, of biomedical signal processing, and I always explain, okay, when we calculate the DFT, the fast Fourier transform, etc. So you must consider only the magnitude, square magnitude, only the magnitude. The phase is not so relevant, okay, because we are interested only in the energy, the power of each specific bands, etc. No, but really for brain connectivity, you have to consider the phase, not the magnitude, okay. But well, no problem because my students from the bachelor are not here, so we can explain that what is important is the phase of both signals. And also the instantaneous phase from each signal can be calculated from several methods, but the most typical is the Hilbert transform. We can see here, for example, this synchronization, this phase synchronization in both signals. We can see these oscillating traces. In this case, that, okay, we have several, this is more or less synchronized. Even here, because it's not so important if this is opposite. What is important is the consistency of the phase during the epoch. Okay, that in this case is very clear that this is very consistent. Here, not, because well, each signal is from her father and her mother, because well, we cannot see any synchronization in the phase. Starting with delay here, It's longer here. So this is the kind of information that we must analyze. There is a very nice tutorial here in order to check and to obtain more information. Here another example, what I explained before. So the synchronization likelihood, well, estimate the likelihood, which is at the same state at two different times. 2 times we evaluate the state, and we can observe in the same 2 times in the other signal the state is also the same. Not comparing, but also that okay, if this is the same, it must be the same. Not between them. This is what is important. The phase is very important, or is more important than the magnitude, because think about that in each electrode, the impedance, the contact electrode impedance can change and also can be different between them. There are some artifacts that you can reduce, but the magnitude of the signals must be not the same in all channels. So everything which is not depending on these variations of the magnitude of the EEG recording, so how you record the EEG, is much better, no? Because you reduce the effects of issues in the experiment. This is why phases is more robust in this sense. Related to this phase synchronization, we have the technique of phase locking value. The phase locking value is the same as coherence, but considering the magnitude of the Fourier transform 1 in all frequencies. This is that, okay, we remove any problem about the energy of different frequencies because we consider always only 1. So we need only this part, okay, from the phases. Another questions, Jean-Francois usually say, my colleague in other question from this one is the phase lag index, or with the wave fast phase lag index. This is what I mentioned before. There are dozens of techniques. In this case, in the phase lag index, well, there is an article, you can, well, nice explanation, but okay, the phase is only considered, as I mentioned before. For example, you can represent the phase of any complex, because remember that here we have complex numbers. It's a complex function. Sorry, it's a complex function. There is phase locking value, but we observe only the magnitude. But the magnitude of something related to the phase. So the phase in any complex number you can represent in the complex plane. Like with an angle, no, and also moving along time. Usually in the first quarter of the plane between 0 and 90 degrees. When you have some noise, you can have even negative phases or more than 90. Well, there are some explanation about this phase lag index is more robust with respect to the noise when you obtain the calculation of this index. Okay. At the end, there are many toolboxes in order to calculate this. So, depending on the crazy you are, you can go deeper to the articles. Another technique is the mutual information. The mutual information we have used several times. This is in the information theory domain related to the Shannon entropy. Okay, so we have one signal, well, 2 signals, X and Y, and the Shannon entropy from the amount of information that we have in one signal, the amount of information that we have in the second signal. Okay, and this is the joint information, the information shared by the 2 signals. Okay, with more area here, there are more connectivity, okay? More relationship between the 2 signals, X and Y. Okay. So So this is explained by means of the probability, the probability. The probability, you know, is the histogram of each signal, and this is the calculation. This mutual information. Well, you have here the article, but this mutual information is interesting, and we have used it because we separated linear and non-linear dependencies. Okay, well, this is interesting because the relationship in the brain, different cortical levels can be linear, non-linear, depending, no, and they are all mixed in the EEG recordings. So, in order to separate this, we use this surrogate data. Okay, the surrogate data conserves all the original information or data statistical properties, but the property of interest that we want to measure. So, for example, we have two signals, they must be ranked, 0 and 1. We generate surrogate data, and we have different surrogate data, and we calculate this cross-mutual information. We obtain the cross-mutual information, the average of all surrogate data, 10 times, probably it's better 50 times. And we have the original and the function from the surrogate data. So we subtract, and we have the final mutual information to evaluate exactly the property we have not conserved in the surrogate data. How we can obtain the surrogate data? This is from a paper of our group, from Jean-Francois' article. It is the thesis. So, for example, this amplitude-adjusted Fourier transform method. Okay, so we have the ranked signal. Well, it's necessary to have a Gaussian distribution in order to apply this, but it's not a problem. If this is not a Gaussian distribution, we can transform, and then we have to cancel this transformation at the end. So we calculate the Fourier transform. We have magnitude and phase from both signals. So imagine that they are the values of the magnitude and the phase, here and here. So in both cases, we maintain the linear, in the magnitude, the linear properties, because we maintain the magnitude in the surrogate data, but the phase is shuffling. In one case, randomly, in both signals, in the ST1, but in the ST2 is shuffling, but conserving the position. We can conserve 3142, 3142, the positions, in order to maintain in the also in the phase the linear property. So using the ST2, we can evaluate the brain connectivity by mutual information from non-linearities. And here, with the ST1, we have both linear and non-linear. I will show some examples using this in later. Okay. And finally, another technique is the Granger causality. Okay. The Granger causality is how we can predict one signal based on the past of the same signal, so the recursive information, but also with the other one. So how the other one contributes to predict the signal. If the contribution is higher, so the connectivity is higher. Okay. Transfer entropy is a version of this Granger causality. We use this, the transfer entropy. So as we use the past and also the other signal, this is a directed method, okay, effective connectivity, because it's not the same from X to Y and from Y to X. And the transfer entropy based on the Shannon entropy is well, this is explained here, is an approach, a different approach to the Granger causality. It is shown here in this article that both Granger causality and transfer entropy are equivalent if we have Gaussian variables. Okay, but we can consider Gaussian variable, Gaussian distribution in the signals, and we can obtain calculate the transfer entropy. Okay, we can move to some examples. So, for example, in this case, we have two examples of drug effect. In this case, alprazolam. This is an anxiolytic. So there is a drug administration here, and we can observe the effects a long time until 4 hours after drug administration. We also have to reference with respect to the baseline. The baseline is in the drug administration, how the brain is changing. Okay. So this case was particularly interesting because we can observe with lines between two electrodes because there was a change in the brain connectivity between these two electrodes, significant statistical changes. Okay, so after 45 minutes, 1 hour, more or less, it is now that is the highest effect of this drug, we can observe here a decrease in the connectivity, here an increase in the connectivity, okay, in different colors. In the case of linear and non-linear, respectively. Okay, we have opposite trends. It was not wrong. So even we correlated with the plasma concentration during these hours, because with blood analytics, we can observe the concentration of this drug on the blood in order to know, and we correlate, well, this is the linear on a long time, okay? And this is in green color, the non-linear. But both are very correlated, but especially the non-linear component with respect to the concentration on plasma. Then the transfer entropy, in this case with ayahuasca. Ayahuasca is a you'll become very happy if you take the ayahuasca. I don't know what to but it's a very strong drug, especially from Latin America. So in the transfer entropy, we observe also from the drug administration, we repeated the drug administration. The participants were very, very happy because after several hours, at 4 or 5 hours, the second administration here in order to observe the effects on the second administration. So in this case, we can observe after 2 hours or 3 hours, especially a decrease and increase, okay, of the transfer entropy. In order to show this is the same, but just to consider only decreases in the third row, the increases in the third row and decreases in the second row. We can observe these changes because if you, well, Sergio, my colleague, saw several participants with the experiment during the night, and well, the participants saw pink elephants during night, etc., flying in the room because it's a very strong drug hallucination. But curiously, in some measures, typical measures, power in the specific bands, they didn't find any change in the brain. So it's very difficult to know exactly what is happening in the brain. But with this transfer entropy, we observe these changes. And also the direction, okay? This is the sources and this is the destinations, the destinations areas of these changes, okay? The sources and the sinks, okay? For example, it was interesting for the neuropsychologists and psychiatrists that in the occipital area, which is more related to the visual aspects, so these are the sources of this increase in the transfer entropy with respect to other zones of the brain. Well, this is some correlations, again, are the same. In schizophrenia, this is comparing coherence and face blocking value. Okay, there's two techniques. It was an auditory oddball task. Okay, you listen to different tones, and there are some normal and also some target tones. Sometimes it's like the visual, oddball visual task, as I mentioned before, but in tones, in different frequencies. So comparing the effect of listen to the tone, the baseline before the tone and after the tone, what is the effect in the cognitive processes in the patients, schizophrenic patients? Schizophrenic are in the columns, comparing with the controls in the right column. Okay, we can observe more effect changes. Okay, this is a statistical maps, changes in the controls and the schizophrenics. Okay, in this both coherence and phase looping value. Okay, in both one. And the last example, I have to go faster. The last example is with the Rett syndrome. The Rett syndrome, we evaluate Rett syndrome is a rare disease, especially for children, girls. And the experiment, we perform active tasks and passive tasks. Okay, passive tasks is, okay, the neuropsychologist explain in the monitor, okay, you can see this, like different games, no? In the active task, the patient must watch specific, for example, some drawings or open a door. They have to fix the attention, pay attention for specific areas in order to something happens in the game. So this is active. And we observe, for example, that in both that type of tasks, different roles, in the coherence, we observe a decrease in the delta band, okay? Before the task and after the task. Okay, but a decrease the delta band. But in this case, with the cross-mutual information, separating linear and non-linear, we are able to, it is more sensitive in the case that, okay, we can observe in the active task some changes, in this case increases in the function, but not in the passive task, what is probably more logical. So, well, I believe more the results, but well, I cannot defend this totally in front of a jury. Okay. So finally, in order to complement the graph theory, because there is a question in the about the graph theory, what is a network? Well, very quickly, we have several nodes, electrodes, different connections. We can obtain the strength of the connectivity using any of the previous techniques. And then a network is created. Okay, we have also a matrix, an array with these values. Okay, with the different electrodes, for example. Okay. We can observe that the strength can be a value or can be 0, 1. Yes, for example, if you have a threshold, you can consider that 1 if there is connectivity, 0. But this is not very common. We usually with the networks. Okay, and directed networks is because it's not the same this electrode with respect to this, and in the opposite, this electrode with respect to this. In this case, it's symmetric, the array, because it's non-directed. But if this is directed, transfer entropy, the strength, we have two values here, from one electrode to the second, and from the second to the first. Okay. Well, there are 7 large-scale brain networks in the brain, very well localized. Depending on your interest and the experiment, you can focus on different areas. Okay, maybe here, the second one is the internal mind, internal processing. So it's relatively important in some diseases. But, well, in this case, the dorsal adaptation network, we have this information in the presentation. You have to move. And we can try to characterize this brain with different measures. Okay, we'll try to be very quickly. But the notation is not important because I will explain the description of it. For example, measures of centrality. Okay, for each node, we calculate the average of connections in each node. Okay, so we repeat this in every channel, and we have the global strength. The average node decrease, the global strength. So the global strength, and then a measure of functional integration. For example, if you want to go from this electrode to this other one, which is the closest distance. Okay, this is the path length. The path length is this, but considering the weights. Okay, distance is the inverse of the weight. If the weight is is high, so the distance is low, no? Because it's very close, because the conductivity is high. So you calculate, it's calculated all paths possible between one and the other electrode, and you obtain the minimum value, the shortest path. And the third measure, and this is associated with global connectivity, because you go from one electrode to another one, but all pairs in the brain, in the electrode. So this is considered global connectivity. But in this case, functional segregation is considered local connectivity. Is how many triangles we can obtain. In this case, for example, it's not a triangle, this is a triangle. So how many triangles we can obtain, and also if this node is shared to another triangle. Okay, so this is the clustering coefficient. Okay, this is the formula, and this is the local connectivity. You have to normalize, because this depends on the number of electrodes you have. Okay, you have 19 electrodes like in the past, so all measures will be lower with respect to 64 electrodes. So you have to randomize, creating surrogate data, moving, shuffling the waves, respecting the connection, but shuffling the waves randomly 50 times, calculating the same measure, cluster coefficients, global strength, etc., and then to average. And we remove the original measure with respect to the average of surrogate. This is like a parameter. Okay, this is something that you have to consider. And we finish with some examples of graph theory. This is an article related to Alzheimer's disease. So in this case, we have epochs of 1 second, okay, and we calculate, in this case, phase coherence. Related to the coherence according to the phase. Again, we have the matrix. In this case, weight value is one color, and we have also topographic plots if we want. And then we calculate, in this case, clustering coefficient and the global efficiency. Okay, the clustering coefficient. Well, I didn't explain the global efficiency. Well, because the other was the global strength. Forget about the global efficiency. I remove here, but I forgot to remove here. Okay, no problem. But if you want, you can go deeper to the article. Okay, but for example, perspective in the results. This is in resting state. Okay, I suppose. Well, Alzheimer's disease, you don't do any gas. Here in the alpha band, we can observe in groups of healthy controls, mild cognitive impairment, Alzheimer's disease, mild Alzheimer's disease, or severe symptoms of Alzheimer's disease, number 2. Okay, we can observe here, not in the others, but in the alpha band, the clustering coefficient, okay, is lower. Okay, so in the clustering coefficient is lower, the clustering coefficient is related to the local connectivity, the segregation, remember. Okay. So it's like the connectivity, the number of triangles is lower, so the connectivity is lower in the patients. Also, we can have topographic maps. In this case, in the alpha band, we can observe that, okay, in yellow is higher than in blue color. Alzheimer's disease, the values in general are lower, as we have here in the bar diagram, but we have the topographic map, and the topographic map are very, very similar, but yes, reducing in average. Interesting. Well, or not, I don't know. In any case, it was published in 4 years ago. I'm sorry. No. Schizophrenia. Okay, in schizophrenia patients, this article was about auditory oddball. Remember that different tones you listen many times. Dark target tones, the probability could be 30%, 30%, 30 to 20% in order to be not to be the target. The connectivity was sorry. The connectivity was relative coherence. This is using the continuous wavelength graph. Okay, so the coherence in frequency was using the continuous. And the graph metric was clustering coefficient and the path length. Okay, we can see the results. We have several groups: controls, schizophrenia patients, perceived episode of patients, and chronic patients. Okay, so we have this, each column is each group. In this case, the cluster coefficient, and this is the topographic maps. This is SPM, the statistical probability maps. When we compare, okay, when you listen to the tone, we compare before the baseline and after the response of this tone in order to obtain information about the cognitive process. So we can observe in the controls there are changes. Okay, there is an increase of the cluster coefficient, more triangles, so more segregation, more connection. But in patients, in the maps we can observe no statistical differences. So problems with the cognitive processes, for sure, because it's schizophrenia. And also, in baseline, the values of the cluster coefficient is higher here in patients, okay, in schizophrenia patients with respect to the clustering because of the hyperexcitability in the baseline, in the normal conditions of this kind of patients. Opposite to the Alzheimer's disease, that the cluster coefficient is lower because of the neurodegenerative disease. But in both cases, the effect of the stimulus is not so strong as in the controls. If we compare populations, control with respect to the other populations, here we observe in the response differences, but not in the baseline, because in the patient don't respond. Okay, this is why we have differences and the controls respond. Another article from our colleague in our group, Saul, in this case, Alzheimer. This is the phase index, the connectivity, and the graph metrics was the global strength, and the path length, and the clustering coefficient. That's the three measures. We can observe here, violent plots, different groups. Okay, in this case, in the global strength, path length, and clustering coefficient. So in the global strength, we can observe in Alzheimer's disease a little bit higher with respect to controls. So in average, the connections is higher. The number of connections and the width of the connections is higher. But the path length is also a little bit with respect to the controls. Lower integration, we have higher path length. So in this case, sorry, the path length is the distance between two electrodes, and is higher with respect to the controls, because the connection is like, okay, I have to get, but I have to get Maribor, so the distance from Barcelona is very, very long, okay, because this is connected, but the path length is very long, because you have to go to differentiate it, blah, blah, blah. So this is not, we have to improve the connection because of the effects in this case. Okay, but happy to be here. The cluster correlation, the cluster coefficient is lower because the number of triangles is, the connectivity is lower in this Alzheimer's. So more or less the parameters show the effect of the disease in the brain network of the respective. This is another article. We have to prepare the manuscript, okay? This is very recent, also with Saul. We use face looking value. To finish, no? Face looking value with continuous Fourier transform. So in this case, we have magnetical stimulation in order to observe the effect of this stimulus repetitively during a long time in patients with respect to the control. So we obtain in this case well, some effects here that you can see in the next article that we will present shortly. And the final one is related to motor execution. There are some people working on motor execution. Also in a study with Saul and Marta. In this case, as we showed before, we asked about, okay, what about the connectivity when you move your arm? Okay, we observe this motor electrical potential, we observe this synchronization and synchronization in the mu and beta band. But what about the connectivity? Because there is not a direct relation that, okay, if you increase the power in a specific band, it's not necessary to increase the connectivity in this specific band because there are different phenomena. So in this case, we observe that in this case, the knot degree or the global strength, path length, and cluster correlation, this is that at the onset of the movement, okay, the decrease of the connectivity is very clear in the mu band, and also in the beta band is consistent along the movement. This is the offset, the end of the movement, It's in a motor execution, okay, not motor imaging. And also the path length, okay, is the global strength decrease, the path length increases because it's more difficult to reach one electrode to another. And the cluster correlation decreases because the segregation is lower. Okay, so thanks to all people of my group, some of them here in Maribor and other in Barcelona. Thank you.